Oh, I gotta switch over to this. Okay. Amber, make sure you talk to me after class. Okay. Oh, okay, we're recording. All right. Okay. So we're working in Chapter 10. And Chapter 10 is specifically about rational expressions, equations, and functions. Okay. Now remember, an expression doesn't have an equal sign. Okay. An expression doesn't have an equal sign. You can't solve it. Okay. You might be able to simplify it by combining like terms, or some ways we're going to look at how to simplify this kind of expression today, to put it, sort of make it look simpler. Okay. And you can combine it with other ones with addition, subtraction, multiplication, or division. So you can combine expressions. You can evaluate them by saying, hey, what if x equals this? Then plug that in and see what it's worth. Okay? But there's no equal sign. You're not solving them. Okay? So a rational expression will define what rational is, that kind of expression. You can't solve it. You're just going to be working on simplifying or evaluating it. Now, if you end up with a rational expression equal to another rational expression, then you've got enough information to solve for x. We'll be doing that by the end of next week. Okay? And of course, functions are when you have an x and a y, two variables that you can then put on a graph. Okay? So we're going to be looking at what a rational function looks like today. We're not going to be doing any hardcore graphing of them, but I want you to see what it looks like, what the family looks like, and some of its characteristics. Okay, so just to start off, defining what we mean by rational. Hopefully you are already familiar with what a rational number is. Okay. The root word of rational is ratio. Okay. And a ratio is just a comparison of two numbers. Okay. That's just really a fancy word for fraction. Okay. A comparison of a numerator to a denominator. Okay. So the definition of a fraction, the definition of a rational number, is that it is the quotient. This brings in another aspect of a fraction. It's quotient. It's a division problem. It's not only a comparison of those two numbers, but it's the top number divided by the second number. And it's the quotient of p, little p, over little q. Okay. Where, let's define what p and q are, where p and q are integers. Remember, integers are your counting numbers. Positive and negative counting numbers. 1, 2, 3, negative 1, negative 2, negative 3. It includes 0, but none of the in-between fractions and decimals. Okay? So if you put an integer on top and an integer on the bottom, you've created a fraction. Now, can p and q be absolutely anything?
Yes.
With one exception.
Not 0.
What can't be 0?
The numerator.
The what?
Denominator.
The denominator. Yeah, it doesn't matter what the numerator is. Numerator can be anything. You can have a fraction with a numerator of 0. Right? That just equals 0. 0 is a real number. Okay? And so a 0 in the numerator means you have 0 of something. Doesn't matter how many slices the pizza's cut into, you've got 0 slices of it. You ate none of it. But it's still a pizza. But q cannot be 0. So q cannot equal 0, because that would make this fraction what? What word do we call that? Undefined, right. You can't divide by 0, and since this is a quotient, a fraction is a division problem, you can't divide by 0 or have a fraction with a denominator of 0, because that makes it undefined. Okay? That means the pizza didn't even exist. Okay? Now, we're going to expand this definition into rational expressions. Now, technically, a rational number, a fraction, is a rational expression, but when I'm saying rational expressions, I mean we're taking the complexity level up a notch, but it's going to follow the same mathematical rules. Okay? So what you know about fractions will apply to rational expressions. We define a rational expression as the quotient. Again, it's a quotient. It's a division problem. Quotient, capital P over capital Q. So instead of lowercase p and lowercase q, which are integers, just numbers, for example, 3 over 5, 3/5, our quotient, capital P over capital Q, our rational expression, we mean where capital P and capital Q are polynomials. Okay. So we spent a good part of, all of this last unit, working with polynomials. We factored polynomials, and we solved polynomial equations using factoring to solve them. Okay? So a rational expression is just two polynomials, one in the numerator and one in the denominator. Separately, it would look like separate polynomials. You put them together in fraction form and you have what's called a rational expression. Just like with a fraction, a regular rational number fraction, Q, capital Q, the polynomial on the bottom, cannot be equal to 0. Now, a rational number, as I said, an example, e.g. means example, might be, say, 3/5. Okay? It's a regular old fraction. What's my P? And what's my Q? And P and Q can be anything, except you could not have that Q. That 5 is fine, but that 5, and that could be a -5 or positive or negative anything, but that cannot be 0 on the bottom. Now, an example of a rational expression might be, say, 3 plus x, there's a polynomial, a linear polynomial. And on the bottom, I'll put another linear polynomial, let's say x minus 2. Now we've got variables involved. Here's on its own, there's a linear polynomial on top, and on its own, there's a linear polynomial on the bottom. And these polynomials might be linear, quadratic, or cubic. They might be other degrees. Okay? In this case, my example is just both are linear. But any polynomial of any degree can be part of a rational expression. Would it be possible for Q to be equal to 0?
0 has to be, or the x has to be 0. You multiply times 1.
Huh? Well, let's explain that first. If x is 0, so we're saying just like here, 5 can't. That 5 it can't be 0. Here, what if x were 0? Now let's plug in 0. So if x is 0, what do we have on top?
3.
And what do we have on the bottom? -2. So we have 3 over -2. Is that a problem?
No.
Mm-mm.
You said the equation equals to 0.
Set which equation?
The denominator.
With the expression, the denominator equal to 0, and so then you would solve for x. What can x not be?
0.
Well, x can be 0.
2.
2, right, yes. Because if x were 2, it's not a matter of what x is. This isn't saying x can't be 0. This is saying the denominator can't be 0. And in this case, an x equals 2 would make the denominator equal to 0. We don't care what the numerator would equal. In this case, it would equal 5. Doesn't matter what the numerator is. If the denominator is 0, it's undefined. And that's something Q can't be. Okay? So that's going to be an important principle moving forward. Keep that in mind. That's exactly what we're going to explore more now. Okay. So these are rational expressions. Rational expressions are used to define define functions. And if a function is defined by a rational expression, that makes it a rational function. To define functions. Okay, so we're coming back to the idea of functions. Now, some functions we're already familiar with working with. Let's say f of x is equal to 3x plus 5. That's the same thing as saying y equals 3x plus 5. Okay. What family does this belong to? What degree is it? What shape does it make on a graph?
Linear.
Yeah, linear. First degree, because the exponent of 1 is the highest degree. First degree, linear expression. This is a function defined by a linear expression. Okay? So it belongs to the linear family, and this function will make a line on the graph. Let's say we have another function, we'll call it g of x is equal to x squared minus 2x plus 5. What type of expression defines this function? Quadratic, right. It belongs to the quadratic family. That's a quadratic expression, So this is a quadratic function because the function is defined by a quadratic expression. It belongs to the quadratic family, would make a parabola on the graph. Okay. The related equation, the related linear equation here would mean you get one solution of x, one x-intercept. The related equation here, you get two solutions for x, two x-intercepts. Okay. What about that? I haven't done it yet. There we go. X plus 2. Okay. What kind of expression is that? I remember what that one's called? Cubic, right. It makes a swoop, like that roller coaster swoop on a graph. Right? It's a part of the cubic family. This is a cubic function because it is a function defined by a cubic expression. Okay? Now, regardless of whether it is linear, quadratic, or cubic, regardless, these are all polynomials. Polynomials are all flat. Okay? Now, let me be more specific. These are polynomial functions. Okay? Functions defined by polynomial expressions. Okay? And you can see that each of these is flat, so to speak. It's just a single polynomial. Okay? Now, as opposed to that, here I'll call this one k just to give it a different letter, but it's a function. Okay? Here's a function defined by, let's use that 3 plus x over x minus 2. Now in this case, we've got a polynomial on top of another polynomial. So what kind of expression is that? Rational, right. Yeah, yes, that's a binomial. That's a linear binomial on top and a linear binomial on the bottom. Because if you just look at them separately, yeah, that's a polynomial, specifically a linear binomial. And the denominator in this case is also a linear binomial. You might have trinomials or 4 terms or 5 terms. You might have higher degrees. That's not important. The fact is that it's a polynomial on top and a polynomial on the bottom, which means this is a rational function. It is a function defined by a rational expression. And the rational function, it's rational expression because it's a polynomial, a capital P over capital Q, a polynomial on top of a polynomial. And those individual polynomials, like I said, they might have any number of terms and any degree, but they're polynomials. Separately, they're each a flat thing. Okay? Now let's take a look at kind of what that looks like and how we would evaluate that. Okay, so far? Okay. All right. So let's say we had just a little quick graph here, and you had that graph. Okay. So that is So this is the graph of a line. So it's a graph of a linear function. Now, what is the domain? Well, going way back, what is the domain of a line, of a linear function? Yeah, exactly. Everything. And what does that mean, domain? That means all of the possible x specifically. Yeah, x values. Remember, range is y values, which is important, but really our biggest focus, the most important thing is what is a domain. Being able to know the domain of a function is really key. So is there any x value that can't be used? No. So our domain of any linear function, except for a vertical line, remember a vertical line is not a function, okay? But any horizontal or diagonal line has an infinite domain. And that domain means x can be anything. Okay? All right, let's consider this. What family does that belong to? All right, quadratic. Okay. First degree, second degree. Okay. Linear, first degree, quadratic, second degree. Linear, if has how many x-intercepts?
2. I mean 1.
Yeah, just one x-intercept. And a quadratic has 2. So if you solve a related linear equation, you get one solution, x, that relates to the x-intercept of the linear function. Solve a quadratic equation, you get two solutions that relates to the x-intercepts of the related quadratic function. Okay? But it's still a polynomial either way, a first-degree polynomial, a second-degree polynomial. What is the domain of a parabola? There's no breaks, right? Now you can't see everything possible, but remember, this isn't always going up and up and up and up forever, but it's also spreading out left and right forever. So you plug in any x, you're going to get a y value on that parabola somewhere. Okay? All x's are okay. You take a quadratic expression, x squared something, you plug in something for x, you can choose anything you want. There's no restrictions. And you will get a y. It'll spit out a y, and that'll be a point on your graph. Okay? So your domain is infinite. And remember, your domain means x can be anything. Okay? Or your domain specifically is what is x can be, and your answer so far is anything. If you have something like that, you have a cubic. Now, that's not only going up and down forever and ever, but it's also spreading out left and right forever and ever. Do you see any breaks or gaps? What's our domain? No breaks. X can be anything. You plug in any x and you will spit out a y, and you will get a point on this graph, whether the point's here or here or here or here or here, or way up here or way down here. Every x will give you a good y that falls on that graph. Okay? So these are all polynomial functions. Polynomial functions. And one of the understandings of polynomial functions is that they have what's called unrestricted domains. Okay. Unrestricted domains. That means that x can be anything. Any real number. Plug in any x, is going to spit out a good y that will give you an ordered pair that's on that graph. Unrestricted domains, polynomial, whether the polynomial is linear, quadratic, cubic, or a higher degree, it's going to have an infinite domain. Okay? And so one way to write the domain is like that. Okay? And that's this was written, the domain, that's the domain in what's called interval notation. Okay. That's how we were used to writing it in the first chapter. We write our domains in interval notation. Another way to write domain, which is going to be more useful for our purposes today, is to write the domain in what's called set builder notation. Okay. Now normally set, you think, okay, set builder, I want you to understand, we really just used in the first chapter, we used set notation to list a domain if it was a finite set. You know, where we could just list numbers. Because when you open with a brace, you know you're about to say, oh, I'm about to have a list of numbers. Well, if your numbers are infinite, you can't list them all, right? So that's usually not very useful. That's often not very useful for infinite lists because you can't possibly list them all. Okay? But, so instead of using pure set notation where we can just list 1, 2, 3, 4, if we want to list something infinite, we're going to use what's called set builder notation. So we're going to build a set with a rule. Instead of listing the numbers, we're just going to build that set with a rule. We still open with a brace. And we say our set, our domain, is all x's. Such that straight line just means I'm about to give you a rule. It's all x's such that as long as it follows the rule I'm about to give you. First, x must be a real number. Okay, so no imaginary numbers. That's sort of a given. We always assume x is a real number. So x is a member of the set of real numbers. Is an algebraic shorthand way to write that. Okay? X is a member. So the rule is x can be all x's as long as x is a real number. And then and then we would list any other restrictions, anything else that's not, that x can't be. But do we have any restrictions on these polynomial functions? No. So we just go ahead and close our set. This is another way to write interval notation, is that way to write the domain, and this is a way to write the domain in what's called set builder notation. Okay. Means the same thing. It means that x is infinite and unrestricted, except it's restricted to the set of real numbers. But we haven't learned about imaginary numbers yet, so that's not our problem right now. We okay with that? Now we get into rational functions, and we already know there may be a problem here. Because we already know there's something that can't be good, right? For example, in this one, what can x not be? So x is restricted. Is there anything else that x can't be? 0 is fine, because that would give us 3 over negative 2. Yeah. Just 2. Just 2. So x is actually still infinite, meaning it can be any real number. That's still an infinite set, except for the number 2. Okay. So we have to be able to write the domain of a rational expression showing what its restrictions are. Okay. So here is a rational function. So a rational function and a rational function, it may have breaks. Okay. And these breaks are, these are places where the graph is undefined. And for a graph to be undefined, it just means that the graph does not exist at that part of the graph. Okay? The graph of your rational function does not exist on the grid at that point. Okay?
You're trying to do the same thing, right? Like the set of x?
Yes.
Yeah.
Right. So you want to know all the x's it can be. So we're going to look at that on the function and then see how we build that. So it's places where it's undefined. And another way of thinking of that is x is restricted. For polynomials, it's unrestricted domains. But x, or the domain, is restricted. Restricted. Okay. So the graph of a rational function, in general, looks like this. You've got part of it that goes forever and ever and ever that way, and then forever, and then it just shoots up or down towards infinity. Okay? And then you've got another part of it that goes off like that, for example. Okay? And there may be some number here, and that dotted line is not part of the graph. I'm putting that dotted line to show you where the graph never touches. As the graph approaches whatever that x is, it's just going to go shoot up forever and ever into positive or negative infinity. Here it's approaching from the right-hand side, and it shoots down towards negative infinity. Now, our eye cannot even perceive how close it gets to that vertical dash line, but it will never touch it. Okay? And even sloppy hand drawing, I can see, oh, it looks like it is, but it's not. It's going to get closer and closer and closer and closer, but it's never going to touch it. Okay? And that's what's known as a vertical asymptote. Love that word. Asymptote. That vertical line I just dashed in is not part of the actual graph. That just visually shows you something that the graph can't be. Can x be over here? Can this be an x? Can this be an x? Yeah. If this is x, you've got a y. If this is x, you've got a y. If this is x, you've got a y. All these x's are good. All of these x's are good. If you've got an x here, you've got a y. You can find a y. You're going to have ordered pairs. If x equals this, y equals that. But if x equals that, no, because I could go up forever or down forever, and I'll never touch the graph. That is an x that will have no y. Let's see what this looks like on the graph. So for example, an example of a polynomial function like we saw before was, let's do f of x is equal to, and this is not really a perfect graph of that, but f of x is equal to 3 plus x over x minus 2. So here's that rational expression we looked at earlier, but now it's defining the function, okay, a rational function. And let's look at what that looks like on the graph. Now, when you enter, now it's already solved for y, so that's good, so you can just enter it in. But when it is rational, this bar means something. You have to tell the calculator, here's my numerator, here's my denominator. So when you enter it in, make sure you lock it up. Okay? So you would enter parenthesis 3 plus x, close the parenthesis. There's my numerator. Divided by, that's our rational bar, the division sign. And then parenthesis x minus 2. Make sure you're using the minus sign, not the negative sign. Okay. Now, make sure your window is standard. So go to window and make sure, oh, and if it's not negative 10, 10, negative 10, 10, mine's not standard right now. So if it's not standard, negative 10, 10, negative 10, 10, then go to zoom and choose number 6, but don't push enter, just push 6. Okay. And that'll give you the standard grid and graph your function. Now in this case, the way the example I drew here actually shot up and then shot down. This one shoots down and then shoots up from the right. Okay? Depends on the function you're graphing, but it has that same idea. Now when you look at yours on your calculator, you might have a vertical line drawn in. Yeah. And that's an artifact, and they seem to be taking it out, so that's not something that shows up. It's an artifact that's kind of the calculator is basically a little confused about how to graph it. Okay, so that vertical line, if you see a vertical line on yours, it's not actually part of the graph. But it does demonstrate where your vertical asymptote is. Okay? And if you have a later version of the calculator where they've taken that artifact out, they've unconfused the calculator, then you won't see it there. Okay? But it's there if you see it, think of it as a dash line. It's not part of the graph. But notice how this graph comes from the left, and as it gets closer and closer to what number? 2. It shoots down into infinity. And our eye can't even perceive, but it's going to go down, 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 down forever and ever. It's going to get closer and closer and closer to x equals 2, but it'll never touch it. And from the right, it goes closer and closer to 2, and as it gets closer to 2, it shoots up into infinity, and it's going to get closer and closer to 2, but it's never going to touch it. Now when I say x equals 2, that's because x, we can't use x. X equals 2 is not part of this graph, right? But think also back to the first unit. When I said x equals 2, that's the equation of what kind of line? Yeah, it's a line. Well, that's because it is a line that is linear. But x equals 2 is what kind of line? Diagonal, horizontal, or vertical? Vertical. Okay? So when we say x can't be 2, what we're saying is that there is a vertical line of x equals 2 that the graph will never touch. And that vertical line, x equals 2, is not part of this graph, but that is that dashed x, that dashed line right there is the line x equals 2. That x equals 2 forms the vertical asymptote, which is not part of the graph. It shows you what the graph will never touch. Make sense? If you go to the table, so if you do second graph, you're going to notice that if you scroll to x equals 2, exactly. That's where your asymptote is. There's an error there because the graph doesn't exist at that point. It is undefined or does not exist at the point x equals 2. And the physical dashed in line of x equals 2, vertical line, is the asymptote, which is not part of the graph but shows you what it can't touch. Now the way we show this domain, we know x is restricted, okay? And x, to show our domain, we say that x can be anything. Okay? I mean, there's infinite x's. We can plug in any x we want